Okay, so in this video, you might have noticed in the previous videos, we kind of have gotten away from the quadratic functions. This right here is now just an example to do markdown of my showing you markdown. But now what I want to do is I want to show how to solve, how to use Sympy to solve systems of equations. So let's say we want to go back up here to quadratic equations, and let's say we want to model the following situation. We have a circle of radius 1 in the xy plane, and we have the line y is equal to x, and we want to find where that line intersects this circle. So let's type this here. When does, let's say finding where a line intersects a circle. So let C be the circle of, okay, I'm going to pause and type this out. Okay, so this is what I have. Let C be the circle of radius 1 centered at the origin. If L is the line with slope 1 that goes through the origin, find where the line intersects the circle. Okay, so geometrically, we might be able to think about this, which is definitely a good way to think through this. If the line is y is equal, so the line with slope 1 that goes through the origin, that has that's y is equal to x, and the circle has equation x squared plus y squared is equal to 1. And so the line is going to intersect the circle when y is equal to x. And that's going to happen when y and x are equal to the square root of 2, or when y and x are equal to negative the square root of 2. That's kind of one way to think through this, but let's sort of write this as a system of equations. So the equation for the circle is x squared plus y squared equals 1, and the equation for the line is y is equal to x. So we want to solve this system of equations. Now this is a nonlinear system. X squared plus y squared equals 1. That's not a linear equation. So we're not going to get, normally when we have two lines, we get exactly, one of three things happens. Either they're parallel and they don't intersect at all. They're parallel with different intercepts and they don't intersect. They're parallel with the same intercept, so they're the same exact line, so they intersect infinitely many places, or they just intersect at one place. Okay, so there's either 0, 1, or infinitely many solutions. Here we've got a nonlinear function, so there's going to be two solutions. So now let's see how we can use Sympy to solve this system of equations. Now there's one thing that I want to point out to you. I've deleted all of the Sympy code, but it's still in the notebook. So for example, if I type x, it's going to tell me that it's going to remember that x is a symbolic variable. This is one dangerous thing that can happen when you're dealing in Jupyter, because you can delete the lines of code where you've defined a variable or whatever, or set a variable equal to something. You can delete it, but unless you do something else, unless you write over it, it's still going to be saved in the Jupyter notebook while the file is running. Once you close it and open back up, it kind of starts everything new. So I'm just going to start from the top. Import. I don't, strictly speaking, have to do this, but I like to always do this just to make sure I'm sort of starting from scratch. And now I'm going to say y is equal to sp dot symbol. I'm going to call it y. You could call this z, and then, for example, let me just do that. And when I print this, it's going to print a z. Okay, obviously, that's a pretty ridiculous thing to do, so let's not do that. So y is going to be the symbol y. X is going to be the symbol x. And so we want two equations. We want x squared plus y squared equals 1, and y minus x is equal to 0, or y is equal to x, however we want to look at it. Okay, so I'm going to say my first function, f1, is going to be x squared plus y squared. f2 is going to be, I'm going to say y minus x, and then I'm going to say equation 1. And again, there's multiple ways of doing this. SP1 is going to be the first equation. So I want F1 to equal to 1. And then equation 2. Oops. Okay, so F2 is my y minus x. So I want y minus x to be equal to 0. In other words, y is equal to x. So I'm going to write F2 0. And then solution is going to be sp dot solve. And I'm going to write this in a vector. So those are these brackets. EQ1, EQ2, oops, comma, that should be a comma, EQ2, and then I'm going to put, again, in vector, the variables that I want to solve for, x and y. And then print solution. And I'm going to cross my fingers and hope that this code is correct. Okay, and it is. And so what this is saying, there's two solutions. The first solution says x is equal to minus the square root of 2 over 2, and y is equal to minus the square root of 2 over 2. And the other solution is x is equal to the square root of 2 over 2, and y is equal to the square root of 2 over 2. Now before, you might remember, I said the solutions are going to be 1 over the square root of 2, 1 over the square root of 2, and minus 1 over the square root of 2, minus 1 over the square root of 2. But notice the square root of 2 over 2 is equal to 1 over the square root of 2. Okay, so that's the solution to these equations. If you do things a little bit differently, it looks a little bit different. I guess that actually doesn't look different, so never mind. And then let's see what happens if I pretty print this. We get something that really doesn't look that much better. I mean, it's trying to do the square root symbol here, but I think this is a little more readable. Okay, at any rate, this is a solution. This is how to find solutions to systems of equations. This is a nonlinear system. Of course, we could have done a linear system as well. I guess let me just do that really quickly. I'm just going to change this. X plus y is equal to 0, and y minus x is equal to 0. So when you get this, you only get one solution. X is equal to 0, and y is equal to 0. Okay. All right. So in the next video, I'm going to show how to do derivatives and integrals. I guess maybe more precisely, derivatives and antiderivatives. And then in the video after that, we'll look at how to solve some differential equations using Sympy.